Hello everyone, I'm Luca Moschella, and today we will talk about relative representations. This is a joint work within my lab, Gladia, at Sapienza University of Rome, and Francesco Locatello. In this work, we are going to analyze neural networks, in particular their latent space, and how different networks embed semantically similar data. So the idea is very simple. Basically, a neural network usually takes some data, embeds it into a latent space, and then uses these embeddings to solve a downstream task. Now, our question is, which is the shape of the latent space? What are the contributing factors to this shape? Ideally, we would like them to be the data distribution, the task, and some hard constraint that we have in the network. But in practice though, the shape also depends on the parameter initialization, the data shuffling, generally random seed, hyperparameters, architecture, and many more factors. Our goal here, is it possible to ignore these uninteresting factors of variation? If the network, the data, and the task stays the same, why the shape should be different? So this is like the motivation of the work. But let's see an example. In the green box, we are dealing with a bidimensional autoencoder. So this autoencoder takes an image in input, produces a bidimensional embedding in this bottleneck, and then takes these two numbers and decodes them in the original image. So in the top and bottom row, there are two different networks, completely independent and trained separately. The only thing that changes is the random seed. So for example, the data shuffling is different and the parameter initialization. In the second column, there is the space produced by these networks at convergence, and it is different. But although different, I'm sure you can see that there are some similarities. It seems to be a rotation in this case. So let's see what we propose in order to unify this semantically equivalent space in order to be also extrinsically similar. The algorithm to compute this relative representation is very simple and builds upon the intuition that the relative distances between these points are almost the same in both spaces. So we start by selecting a subset A of the training set X denoted by anchors. So for example, we select in this example, two images, two digits, and embed the same digit in both spaces and obtain one anchor, the yellow anchor. We take another image and obtain another two embedding, one for each space, the blue anchor. So those are in correspondence. And we used an encoding function that must be known to embed the data. Thus, we choose a similarity function, an arbitrary similarity function. In this example, the Euclidean distance, to compute the distance between the sample embedding and each one of the anchors embedding. Thus, we represent the sample in terms of these distances and obtain this relative space on the right. And as you can see, it is much more similar than the original space. Basically, we are expressing data in terms of their similarity to a fixed sets of anchors. So we are expressing data in terms of other data. In the bottom part of this poster, there are three different applications. Let's start on the left with the semantic alignment. Here we are dealing with words, English words, and two types of word embeddings, completely independent. A word embedding is a way to represent the meaning, the semantic of a word into a vector. So in this case, each point is a different word, and each color is a semantic area. For example, the blue dots are words that are related to cars, the green dots are related to animals, and so on. And as you can see, the original space, what we call the absolute space, are very different, completely different. But if you perform this relative transformation, using the same anchors for both spaces, they become extremely similar. Meaning that in this case, and our assumption is that most often, if the semantic content of the data is similar, they are going to be represented similarly in the relative space. The second application is the zero-shot stitching. In this case, we are dealing with encoder-decoder models, and in particular, in this example on the poster, with a generation, a reconstruction task. So in this case, it is an autoencoder, but in the paper we also show this with classifier. So the decoder is trained on the relative representation. You can do it because it's completely differentiable. And once these two independent models are trained, you build a new model stitching together the first encoder and the second decoder without any fine-tuning or retraining. If you use a normal autoencoder as the original pipeline, the new stitched model is completely broken, as you can expect, because the neural components are independent, so they cannot really communicate together. If you use a variation autoencoder, is a type of autoencoder that forces the latent space to have a certain distribution, a Gaussian distribution. You can see that the reconstructions are realistic because each point is regularized, so it makes sense whatever the decoder that you use, but it's wrong because it's the wrong semantic. So a point in the first space can be reconstructed realistically with the second decoder, but the meaning is not compatible because maybe there is a rotation, so the meaning are rotated, and an 8 is being reconstructed as a 7. With a relative autoencoder, everything works fine instead. In the paper we also show that this technique can be used even across languages. For example, you can train a classifier on English with feature extract with a pre-trained English transformer and reuse the same classifier without fine-tuning on Japanese, using a Japanese transformer to extract features and reusing the classifier without having to train a Japanese specific classifier. The latent application is the latent performance metric, and in this case we are on graphs, in particular on node classification on the Cora dataset. Here we assume we are given a very good reference model, the orange dot, and it's very good, so very high on the performance axis, and it's very similar to the reference model because it's itself, so right on the x-axis. We perform a huge grid search, changing many hyperparameters, architectures, many optimizers, random seed, number of epochs, and we obtain 2000 models once they are finished training. So we train 2000 models, each one of these blue dots. And we observe that there is a correlation. Basically, if you have a model that is similar in the relative space to the reference one, that model is good in the downstream task. So this is like a proxy to evaluate downstream performance, only looking at the latent space. And this correlation also holds over time. On the right part, for example, you see 9 different models getting trained, and there's a strong correlation between the performance and the similarity to the reference model also there. And it's also open many research directions. For example, one can imagine a teacher-student setting where the student network is getting trained to enforce a latent space that is good because similar to a reference one. So a latent teacher-student setting. Yeah, that's it. So if you have any questions, feel free to ask me at Synapse or via email. Thank you so much and goodbye.